Our next functional group is amides, and we're going to start with the nomenclature of our amides. When we go to name an amide compound, we're going to drop the oic acid from the parent carboxylic acid name, and then we're going to add amide to the end of the name. So for the first compound, my parent name would be benzoic acid. So when I drop the oic acid and add amide, that gives me benzamide. For the next compound, the parent carboxylic acid would be ethanoic acid. So when I drop the oic acid and add amide, I get ethanamide. And in the third one, we have a 5-carbon parent chain. So when we drop the oic acid and add amide, we get pentanamide. Now, there are lots of different types of amides that we will need to name, and these first 3 examples here all have a nitrogen that's also bonded to 2 hydrogens. We can also look at compounds like these here, where the nitrogen in each of these examples has alkyl groups bonded to it. So we'll need to include these groups in the substituents for our name. Here the nitrogen has 2 ethyl groups that are bonded to it. When it comes to naming this compound, we have a 4-carbon amide. So our parent carboxylic acid would be butanoic acid, which is going to give me butanamide. As the parent name for this compound. Now, when it comes to naming those ethyl groups that are bonded to the nitrogen, we're going to name those ethyl groups just like they were a substituent off of an alkyl chain. And instead of using a number to indicate the point of attachment for the parent name, we're going to use the letter N to represent the fact that it's bonded to the nitrogen of our amide functional group. So in this case, this first substituent here would be an N-ethyl. The second one would also be an N-ethyl. And what we know from way back in the beginning of the semester is that we can only have ethyl listed 1 time in our substituents. So what we're going to do is just like we did way back in the beginning of the year, we're going to name this as N-N diethyl butanamide. N-N diethyl butanamide for the name of the compound. In the next compound, we have an 8-carbon parent chain. The substituents that we have to deal with in this compound are a methyl group at carbon 5, an ethyl group on the nitrogen, and a phenyl group on the nitrogen. So if I list those substituents, I have a 5-methyl, I have an N-ethyl, and I have an N-phenyl. So when I put all of that information together, I'm going to alphabetize according to the first letter of the substituent. The N for those groups bonded to the nitrogen act just as a number, so they do not factor into the alphabetical order at all. So the name of this compound is going to be N-ethyl, 5-methyl, N-phenyl, octanamide. So N-ethyl, 5-methyl, N-phenyl, octanamide. Next, we're going to look at a different type of amide functional group, and that's a lactam. If we have a cyclic amide, that is a functional group that we call a lactam. Here's an example of a lactam in a 6-membered ring and a 4-membered ring. Just like we saw with esters, when it comes to naming these lactams, it's going to be based on the distance between this carbonyl and that nitrogen. So we're going to use our Greek letters in order to note that. The first one becomes alpha. The next carbon is beta. Then we have gamma. Then we have delta. So that this 6-membered lactam is what we call a delta lactam. For the 4-membered ring, this is my alpha carbon, and that's my beta carbon. So this lactam is what I call a beta lactam. A beta-lactam is an important functional group because this functional group is key to the activity of penicillin. When it comes to the reactions of amides, there's a few things you need to remember. First is that our amides are very unreactive. They are the least reactive of our carboxylic acid derivatives. They're going to require acid activation or the use of strong nucleophiles in their reactions. The other thing that you need to remember that we'll get into in more detail in just a moment is that when it comes to amides, you always need to watch your pH. And we'll talk about some of the cases where that comes into play in just a moment. So if we use this compound as a simple amide to look at a couple of reactions. We could look at the reaction of this amide with H3O plus in heat, and the product of that reaction is going to be a carboxylic acid plus an ammonium ion. We could also look at the reaction of that same amide under basic conditions, so that if I treat that amide with sodium hydroxide, water, and heat, the product that I get out of that reaction is a carboxylate ion and an amine. The third reaction that I could do with amides is the reaction with an alcohol, acid, and heat, and that's going to give me an ester and an ammonium ion. So one of the reasons we have to be so careful with our pH is that in each of these cases, our product is an amine or an ammonium ion. Under basic conditions, this reaction in the middle, we got the neutral amine. But under acidic conditions, we ended up with the ammonium ion as our product. We also have to be careful with our carboxylic acids and their pH. When we have this reaction and make a carboxylic acid, because we're under acidic conditions, that carboxylic acid remains in its protonated form. But when we run a similar reaction under basic conditions, notice that that carboxylic acid is deprotonated and present as our carboxylate ion. I want you to work through the following two mechanisms for homework. So anytime we have an amine and a carboxylic acid involved in our reactions, we really have to watch our pHs. So if we have a carboxylic acid, under acidic conditions, our carboxylic acid is going to have the proton, which means it will be in its neutral form. When a carboxylic acid is under basic conditions, it's deprotonated. When we have an amine under acidic conditions, it's going to be protonated and exist as an ammonium ion. And when we have an amine under basic conditions, it's going to be neutral. So always watch your pH with carboxylic acids and amines. So if we look at the mechanism for the conversion of an amide to an ester, this is an acid catalyzed mechanism, and so we can look at this amide and we can look at its resonance. We know that we always have a resonance structure that pulls those electrons up to the oxygen to give us a positive charge on the carbon and a negative charge on the oxygen. This structure has an additional resonance structure where the lone pair on the nitrogen can be pulled towards that carbon, giving me this structure. And what this series of structures shows you is that the oxygen in this amide structure has the most electron density, so this is going to be the most likely atom to pick up a proton under the acidic conditions of this reaction. So going back to the mechanism, if we have this under acidic conditions, the carbonyl can protonate, and when that happens, that gives me this structure. This is my activated amide. In this activated amide, the carbon of this structure is a much better electrophile than in my neutral amide. So now my methanol can come in and attack at that carbon, push the electrons up to the oxygen, and give me a tetrahedral intermediate. So in this tetrahedral intermediate, just like all of our tetrahedral intermediates, it's important to analyze the best and the worst leaving groups that we have. In this structure, the three possible leaving groups that we have are a hydroxide ion, an amide ion, and a molecule of methanol. That means that if this OH left, it would leave as a hydroxide ion. If the methanol left, it would leave as a neutral molecule of methanol. And if my NH2 left, that would leave as an amide. Now, under the conditions of the reaction, these are our three possible leaving groups. This reaction is acidic, and under acidic conditions, we're not going to have hydroxide or this amide ion leave. They're way too basic for that to happen. So that's not an option, that's not an option. So in this tetrahedral intermediate, my very best leaving group is this molecule of methanol. But this is the structure that I need to keep in my product. And remember that all of these reactions are reversible. All of these reactions are going to be in equilibrium and driven by Le Chatelier's principle. So in order to keep this alcohol bonded at that tetrahedral intermediate, I need a base to come along and remove that proton. So I could use a base like a molecule of water to remove that proton, give the electrons to the oxygen, and that's going to then give me the next intermediate. So here's my next tetrahedral intermediate, and if I analyze its leaving groups, that would be hydroxide, the amide, or a methoxide ion. And all of those are bad leaving groups under the very acidic conditions of this reaction. Under acidic conditions, we're going to have neutral molecules depart this tetrahedral intermediate. That means that we need one of these groups to pick up a proton from the acid in this reaction in order to become the best leaving group. So in this case, if the nitrogen picks up that proton, we get this structure. So now from this tetrahedral intermediate, my leaving group choices are hydroxide, methoxide, or ammonia, NH3. And as we've said, under the conditions of this reaction, hydroxide will never act as a leaving group. Methoxide will never act as a leaving group. So now ammonia is my best leaving group, and that's exactly the group that I need to leave from the tetrahedral intermediate. So what's going to happen is that the lone pair on one of my oxygens can help kick out that nitrogen, or I can show the nitrogen just taking its electrons and leaving. Either way is fine. So in this case, I can show that oxygen's lone pair kicking down towards the carbon of that tetrahedral intermediate, kicking out my best leaving group, and that gives me this structure. This is an activated ester. I also lost a molecule of ammonia as my leaving group. And so now the only difference between this intermediate and my final product is that I need a base to come along and remove this proton. Remember that amines are good bases. They're going to be the best base you have in this reaction, so it's highly likely that that amine is going to remove the proton from that oxygen and give us our final products. Our final products are going to be the methyl ester and the ammonium ion.